So for folks who are not on, remember, I do want to see notes. So make sure you're taking notes from this. Despite us being not physically in school, this is the crazy time of year for me as far as being busy. There's a lot of responsibilities that I have. So it takes me a little bit longer to get grading done. I apologize. I'm working on it. I'm prioritizing grading as much as I can. But please be patient with me. I know some of you are more patient than others, and I do appreciate that. But I want to give you feedback on what you've turned in, mostly so that you know how you're doing in physics. That's really what it's about at this point. So momentum, it keeps us going. So what is it? Let's watch.
Momentum is inertia in motion. A lot of momentum means a lot of oomph. An even better way to describe momentum is as the product of mass times velocity. This means that if something is moving, there are two ways to affect its momentum. One, there's the mass. You know, for the same speed, a massive truck has so much more momentum than a mosquito. And two, look at the velocity. A baseball thrown gently by a kid will be easy to catch. That same baseball, thrown at 100 miles per hour, might knock you over. So a tiny bullet at a high speed has a lot of momentum. Wear a bullet vest and it'll still knock you over. An oil tanker creeping along at only a few miles per hour also has a lot of momentum, not by virtue of its speed, but by virtue of its great mass. Because it has so much momentum, so much inertia in motion, the tanker can't just pull into the dock. Rather, it's greeted by powerful tugboats that help to manage its maneuvering. A fast-flying tiny bullet and a creeping massive oil tanker are both difficult to stop. Both have a lot of oomph, that is, a lot of inertia in motion, which you now know to be what we call momentum. Good energy.
All right, as we just saw, and continue to hear.
Momentum
apparently,
is inertia in motion. A lot of momentum means a lot of oomph. An even better way to describe momentum as the product of mass times velocity. This means that if something is moving, there are two ways to affect its momentum.
I have no idea how it's still playing.
There's the mass. You know, for the same speed.
All right. That's funny. Apparently 2 videos played at the same time. Okay. So as we just saw, momentum is equal to m times v, mass times velocity. Some of you said acceleration, some of you said speed. Here's why it's important that it's neither acceleration nor speed. As we know, acceleration is a change in velocity, okay? So it's not measuring the change in velocity. Momentum is just measuring that velocity. But momentum has a direction, and that's critical. So that's why it's not mass times speed, that's why it's mass times velocity. And we represent momentum with the letter P, lowercase p. I don't know why. I'm sure you could probably Google it, figure out why. I've never actually been curious as to why. It's just like momentum is P and then we move on. So that's where I've always stopped. But I I actually would be interested to see if you found out. Momentum is a characteristic of a moving object that's related to the mass and the velocity, okay, and directly proportional to both of them. It's not velocity squared, it's not mass squared, it's just a simple relationship, okay? And then the unit, because we're multiplying kilograms times meters per second, the unit is kilogram meters per second, or Newton seconds. I'm sorry, that should be newtons per second. I don't know why that says, oh no, that's right, Newton seconds, because kilogram meter per second squared is a Newton. So the units are either Newton times second or kilogram meter per second. And as I said, it is a vector, direction as well as quantity. Now, there is a relationship between momentum and kinetic energy. We, over the past couple of weeks, started to use this idea of kinetic energy, moving energy. Kinetic energy does describe the motion of an object, and in addition to momentum, any change in mass and or velocity will change both of these things. The more momentum or kinetic energy a moving object has, the harder it is to stop. But the big difference between momentum and kinetic energy is if you look at the formula, look back at the formula for kinetic energy. I know we didn't do a lot with it, but if you look at that formula, kinetic energy, and I'm not going to type it because unfortunately it's hard to do the squares and everything. All right, kinetic energy is 1/2 mv squared. Now, the 1/2 is important for sure. The more important thing is this velocity is squared, whereas with momentum, it's just mass times velocity. So in order to determine how much energy something has, that velocity is doubly as important. Okay, there's one more component of velocity. But for momentum, mass is equivalent to velocity as far as influencing how much momentum something has. So that's the biggest difference between momentum and kinetic energy. Kinetic energy is heavily dependent on velocity, whereas momentum, they're both equal to each other as far as their influence on the actual quantity of momentum. So the relationship between momentum and mass. The more mass that an object has, the more momentum it has. For example, you can catch a football moving at 20 meters per second. I mean, that's fast. That would be 1 second to travel about 20 yards, all right? So that's a fast pass. But you cannot stop a car moving at the same speed. If that car is moving 20 yards over a second, that's going to be you being flat. And that's because of that mass difference, all right? Just like more force is needed to stop a baseball thrown at 95 miles an hour than to stop a baseball thrown at 45, even though they both have the same mass. That would be that velocity difference, all right? So if mass stays the same, but velocity changes, that impacts momentum just as much as if mass changes, but velocity stays the same. So as I just said, the velocity of an object also affects the amount of momentum it has. So an arrow shot from a bow has large momentum because even though that arrow has a small mass, it travels at a high velocity, just like the gun, the bullet traveling from the gun through the apple that we saw in the video. So let's do some calculations here. Quick momentum calculations. What is the momentum of a bus of mass 9,000 kilograms and velocity 16 meters per second, a car of mass 1,800 kilograms and velocity 80 meters per second? So first of all, what's our formula? Well, you got a unit along with a measurement. So what's the formula for momentum? Including the letter that represents momentum. Those are the units. But what are we multiplying? And what is the letter that represents momentum? Okay, let's start with the formula. Thank you. All right, P equals m times v, momentum equals mass times velocity. So the mass of the bus, as I see here, is 9,000 kilograms, don't forget units, times, as I see someone commented, 16 meters per second. And what do you get when you multiply that all out? Please don't forget units. All right, so I'm seeing this kilogram meters per second or Newton seconds. And what I see as far as significant figures, I know the 16 is significant, I know the 9 is significant. So really, if I wanted to be very cautious about my significant figures, this would be 100,000 kilogram meters per second. If I told you that the bus's mass, that first zero, so 90 was significant, I think that'd be reasonable to say that the momentum is 140,000 kilogram meters per second for that first one. And then let's do the car. So momentum equals mass times velocity. What are we looking at here? Spell it out. Thank you. 1,800 kilograms times 80 meters per second. Surprise, surprise. We're left with the same thing. And if we assume 2 significant figures throughout, which is probably a reasonable assumption for these numbers, then we get the same product, meaning that these 2 objects have the same momentum. The bus that is traveling at 16 meters per second, let's be clear about what that means. That's about 50 feet every second. Okay, if you can visualize 50 feet, it's in the suburbs, it's the typical lot size. Lot size is about 50 feet long. In 1 second, which that's not all that fast, versus a car going 80 meters per second, that's really fast. Okay, that's really fast. That's almost 300 feet per second. They have the equivalent momentum. All right, so then let's solve this last one. Which has more momentum, a 3 kilogram sledgehammer swung at 1.5 meters per second, or a 4.0 kilogram sledgehammer swung at 0.9 meters per second? So, again, let's always start with the formula. Work this out on your own, please. And let me know in the chat which one has more momentum. Good, I'm seeing some good answers here. Save some space. All right, that's Newton seconds, by the way. That's that unit, just to save space. 4.9, 4 times 0.9 is 3.6 Newton seconds. So the 3 kilogram sledgehammer swung at 1.5 meters per second has more momentum, okay? Now, I don't expect these calculations to be difficult for you. And so if you're like, wow, this is really easy, that is the correct response. You should be thinking this is really easy to calculate momentum. That is not what's difficult about momentum. What's difficult about momentum is figuring out the relationships, figuring out how to set up these problems, how to set up the calculations as you're going to see, as you see collisions happening, right? And it's not even really all that difficult. Last week with waves was far more in your head than this is. This is very much rooted in reality that you are accustomed to seeing on a daily basis, okay? Any questions about these calculations? All right. So we'll stop there for today. And I want you to head out to the collisions lab. I did forget to tell you to have the lab table open as well. You're going to need that open, not immediately, but you will need that open. And also making sure that you've clicked on the collision lab. Now, one trick with that is this is Flash. So some of you may have some problems opening the Flash animation. If you do, make sure to activate Flash. Chrome might ask you, if you want to allow Flash to run, and you want to say yes, depending on what device you're on. Good afternoon, Aisha.
Good afternoon. Hi, Mr. Dutton. Hey, back.
Hi. Good afternoon.
You can't see?
I can't see you.
Oh.
Yeah, depending on your Flash situation, you might have to might have to play around with it. I'll open a pop-up window. But let me know in the chat if it's not working for you. Try to work through it. The alternative here is that you can work with a partner. And so if you are unable to if it says plugin blocked, you should be able to unblock it. So let me see if I can show you an example of that. Again, if you continue having problems, if any of you continue having problems, I'll just have you pair up. So let me find another one just to show you what I go through. Density, there we go. Oh, I must have seen this one before. Oh, I did, of course. Okay. No. Now it's just very happy with me and this website. So once you have Flash activated for the website, it should be fine. Again, if you have problems, let me know. We'll work on it. Okay, so for this lab, you're going to want to stay on the Introduction tab. Don't go to the Advanced tab. You can, but if you go to the Advanced tab, that allows you to add more objects and allows you to operate in 2 dimensions, and we don't need to do that quite yet. So there are lots of options on here, and if we just go with the defaults and we hit play, we see that there is a collision, and after this collision, objects 1 and 2 move away from each other, and each of them has a velocity vector, and each of them also has a momentum vector that is dependent on their mass and velocity. We can also view the center of mass of the entire system, which is an interesting way to think about how a system works, because that center of mass is showing where the average center of objects 1 and 2 is as they move apart from each other. It's not something that we're going to do a lot with, but it's interesting to see. There's a momenta diagram. That momenta diagram is showing us the momenta, which is the plural of momentum, of the system, so that we see that the momentum of mass 1 is to the left and is small. The momentum of mass 2 is to the right and is bigger. And the total momentum of the entire system is actually pointed to the right because the momentum of 2 is greater than the momentum of 1. You can zoom in or out in order to get a better look at that. We can also view the kinetic energy, and we can show the velocities and momentums, the values, so that we can see what those are. Now, another way to show those values is to click on More Data. If you click on More Data, which you're going to want to do, then you'll be able to see and manipulate the masses of each object. Right? If I change that mass, all of a sudden it's huge. You can view, can you manipulate? Oh, apparently you can't manipulate the positions. I hadn't played with that before. Don't manipulate the positions. You don't need to for this lab. And you can also view and change the velocities. That will be helpful for when you change the initial velocities before you start the collision. So if we click restart, it starts us off with mass 1 being 1/2 kilogram, mass 2 being 1.5 kilograms. And the velocity is 1 and 0. Now we can start it off where 1 is at 1 meter and 2 is at 2 meters. And then we hit play and we see the collision happen. If you want to see it in slow motion, you can decrease the sim speed. If you want to see it just go crazy, increase the sim speed. You can also step through it so that it shows you each like 100th of a second or so. All right. And then if you mess up too much, hit reset all, and that'll get you back to where you started. Make sure you click on more data so that you can manipulate the mass and the velocity. And as always, it's always fun to play around with the sound. Oop. For this first lab, you're going to keep elasticity at 100%. Elasticity means how bouncy something is. So this collision, there's basically going to be no friction in this collision. All the momentum will be kept as velocity. It will not dissipate as heat. It will not be lost to friction. So that's how to use this sim. If we go to the directions, number 1 is just the link. Number 2, I described to you. Number 3, I want you to play around with this with mass and velocity. You're going to be using the collision lab table, this one here, to record all of your data. For this first part, you're going to be doing trials 1 through 8. Trial 9 is just going to be for number 5, part E. Trials 10 through 13 will, I'm sorry, 10 through 12 will be for the last part. You want to record the masses of 1 and 2 in kilograms, the initial velocities of mass 1 and mass 2. For every trial, you're going to want to calculate the initial total velocity. Remember that if one mass is going in the opposite direction as another, that's going to have to be a subtraction. If they're both going in the same direction, then that's going to be an addition. You're going to want the initial total momentum. Well, you got momentum over here, so it's calculating it for you. And then once it's over, and really after the collision is over, you don't have to wait for it to go off the screen. Once the collision is over, then that velocity is not going to change. So this final velocity was negative 0.5 meters per second and positive 0.5 meters per second. So final velocity 1, final velocity 2, and then my final total velocity, and then final total momentum. Now, I'm asking you to do 8 trials, and in number 4, I'm describing what I want those 8 trials to be. It's up to you what you want the masses to be, but for the first trial, I want masses in 1 and 2 to be the same. However, the velocity of mass 2 should be double that of the velocity of mass 1. For the second trial, again, keep masses 1 and 2 the same, but the velocity of mass 2 should be half that of mass 1, and so on and so forth. Recording everything in the collision lab table. questions? We are not doing 3 trials of each thing, and that's a great question because this is a simulation. And it's not reality. In reality, we have real forces and we have real error and we have real human error. There is 0 human error. There is 0 reality here. So there is 0 chance that doing things multiple times will result in any differences. We don't have to average anything. What we're doing here is we're playing around with the simulation in order to determine what the relationships are among mass, velocity, total mass, total velocity, and momentum. All right, so go ahead and get started if you haven't already, and keep the questions coming on the chat.